Graphing a rational function is quite a task. If we really don't have a clue as to what to do, we could call ourselves Nax. Okay, well, let's do it. Is the top and bottom factored already? Yeah. What is the domain? There is a domain issue with x in the bottom. We would find the value of x that is restricted from the domain by setting that denominator equal to 0 in solving. Subtract 1 from both sides. Divide by 2. Ooh, negative a half. That is the one value of x you can't have. It is the only value of x restricted from the domain. Okay, keep that in mind. X cannot be negative 1/2. If x can't be negative 1/2, then that is going to be the vertical asymptote. The boundary. The place where your graph can't go. It gets really close to x's negative 1/2, but no touching. What about a horizontal asymptote? To find this, we would compare the degree of the numerator with the degree of the denominator. See an understood power of 1 up top, understood power of 1 down low. The degrees are equal. When that happens, you find the equation of the horizontal asymptote dividing the leading coefficient from the top by the leading coefficient in the bottom. So y equals 2. This is going to be a horizontal asymptote. Our graph will get really close, but no touching. Will there be a slant asymptote? Not if there is a horizontal asymptote. You never have a slant and a horizontal asymptote at the same time. As for finding the y-intercept, we do that putting a 0 in for x. When we do, we find the y-intercept is 1. Okay, that would be, oh no, I lied, it's negative 1. That would be the point on the y-axis. To find the x-intercept, we put a 0 in for y, or we can take a shortcut, setting the top equal to 0. I would add 1 to both sides, divide by 4. I find that the x-intercept is 1/4. That's the ordered pair, 1/4, 0. So I've got the boundaries, or asymptotes. We have some intercepts. We need to find some more points to sketch this graph. Keep in mind, there still is a domain restriction. You would choose values of x that are bigger than negative 1/2 and smaller than negative 1/2. When you do, well, an x of 0 goes with a y of negative 1. If x is 1, y is 1. When x is 2, y is going to be 7/5, or 1.4. If x is negative 1, y is 5. When x is negative 2, y is 3. And x of negative 3 goes with a y value of 13/5, or 2.6. Don't forget that x-intercept is 1/4, and the y-intercept, again, is negative 1. Time to graph. We can plot those points, the intercepts where x is 1/4 and y is negative 1. Let's also draw in our boundaries. That vertical boundary occurs where x is negative 1/2, the graph cannot go there. Where y is 2, the graph cannot go there, which raises the question, where does the graph go? We have a point, our y-intercept, our x-intercept, and x of 2 meets a y of 1.4, and x of negative 1 meets a y of positive 5. When x is negative 2, y is 3. If x is negative 3, then y is going to be 2.6. Looks like we can connect these dots to get the shape of a rational function that is approaching these boundaries, but no touching. The challenging task. The challenging task is done. No touch. Stop.